Okay, I'm going to go through a couple examples here of some how you can reduce some of these equations using Boolean algebra. This will be something that you'll be doing in your homework also. I'm kind of putting this sheet up here just as kind of a reference, a little bit of a cheat sheet. So if we need to refer to it, we can look at it at any point, or I can point out some of these rules. So let's take a look at an example here where we have an equation. For example, in this case, x is going to equal a and b naught and d, or a and b naught and d naught. Okay, so one of the first things you want to do is try to identify what commonalities we can factor out of this. And pretty quickly, get another color here, pretty quickly we can see that we've got a common term here. This AB naught and AB naught. Now sometimes, you'll have to pardon me, sometimes when instead of saying A and B naught, I'll say AB naught, because that's kind of the way you would look at it. But it's probably more proper for me to say AB naught, A and B naught. Okay, so we can factor that term out of the equation and write it like this. A, B naught, ANDed with D or D naught. Okay, now what you need to try to identify is which, if we take a look at D or D naught, it kind of looks suspicious, like there might be something wrong there. And if we take a look down in the corner here, it's the same thing as A or A naught. So what did that reduce us to as a 1? So if we write the next step of this equation, it'd be written as A and B naught and 1. Okay? But anything ANDed with 1 over here is that original term. So A and 1 is A. So that 1 basically goes away and we're left with A and B naught. Now, as you start to do these circuits in the lab, which we should be able to get all the parts to you next week, you'll start to see very quickly how nice it would be to make a circuit that looks like that compared to this top term. And when you're doing this process of reduction, that's the whole point. We're trying to get rid of unnecessary gates and even sometimes try to get to the same logic type or family. Okay, for our next one, we're going to again use this equation x equals here. Sometimes they don't show an x, but you just have to do the reduction. We have A naught or B, and that expression ANDed with A or B. So anytime you see this expression here where we've got these two terms that are ANDed together, so we have this first term here ANDed with this term, it kind of is screaming to do the distribution here, to actually create these 4 separate terms. And so again, we'll use this FOIL method and kind of multiply these out to find out what we end up with. If you're a visualizer, you could probably visualize this and pretty quickly see what this could reduce to. I'm not the greatest at that. It takes a bit of practice. But let's multiply these terms out. So the first terms here, we'd have A naught and A. So that's the first, the outside two terms, A naught and B. Inside, B and A. And finally, B and B. Sorry, I've got some better markers on their way from Amazon. Bear with us as I finish this up today. Okay, so let's see what will happen here if we can reduce any of these. Well, A naught and A is going to equal 0, because with an AND gate, if the terms are opposite, there is going to be there's no way you're going to ever have a 1 output. So that basically goes to nothing. And the same thing, or something similar, with B and B. Okay, anytime we have two terms that are ANDed together here, the third one down here, A and A is A, that ends up equaling B. So let's rewrite this here. We have A naught B coming from this term, or, and I'm just going to go ahead and flip these two. We'll see why in a second. But based on the commutative property here, we can just switch those terms. It's like switching the inputs to a gate. A naught and B, or A and B, or B. Now take a moment and see if you can think of what is common between these three terms here. It's pretty quick to see there's a B here, a B here, and a B here. Can we factor that out from all three of those? And the answer is yes. So we can now have B ANDed with A naught, or A, or what's the third term? We're factoring B out of it, so it ends up becoming a 1. Now what's interesting in this case is that anything that is ORed with a 1 is going to become a 1 based on the second equation here, even if there are multiple terms here. So what this ultimately reduces to is that all of this falls away and we're left with just the B term. So in this equation, this is actually becomes a more kind of advanced, it's almost like a proof in a way. Anytime you have these terms that are ANDed together that have the A naught and the A, basically that A term is not relevant in it and it just becomes the B input. Kind of an interesting one there. Okay, for the last example here, I'm going to write out an equation, x equals A and C and D, or A naught B C D. Now, because these are two ORed terms, we can't use the FOIL method to distribute it. So typically when we're looking at these, we want to see what can we factor out that's common between them. So if we take a look at it carefully, we can see there's a CD there and a CD there. So let's see if we can pull that out of the equation. We can write this as C and D ORed with A or A naught B. If I hadn't already mentioned it, I'm getting some better markers, so they shouldn't look so huge here. Okay, now, based on the last video, we discovered that this term here, A or A naught and B, can be reduced to simply A or B. So that's one you want to kind of keep in mind. If you see that, that'll pop up. And we're ANDing it with C and D. That hasn't changed, so we're going to have C and D here ANDed with this term. Now, the way that this is drawn here is the ANDing of two expressions here, kind of like this. We've got our CD and we have our A or B, and these two terms are basically ANDed together, big AND gate. Okay. You'll hear sometimes that an ANDing function is referred to as a product, and that's because it looks like multiplication. If you look at the dot here, okay, or sometimes if the letters are written together, that's often referred to as a product. It's not exactly multiplication, but that's what they call it. And the OR gate, the OR function, is referred to as a sum. That's, again, when you see the addition sign there. And if it actually some of these same properties kind of fall through when we're looking at the equations. But we refer to that if we're ORing these two terms here, or ORing a couple of terms, let's say it's AB and the output is X, that would be referred to as a sum, okay, of those two terms. And the one on the top here is referred to, whoops, running out of space, that's referred to as a sum. And when you AND two terms, it's referred to as a product. So in this case, we have these two terms here, CD and A or B, C and D ANDed with A or B. This would be called a product. Well, it's not really a product of sums, but it's a product of two terms. Okay? My point here is that we can also represent this in another way. If we redistribute the values out, you don't have to do this, but this just shows you there's an equivalency here. If we basically redistribute these values, we'd have CD and A or CD and B. And now what we have here, these terms on the left and the right are ANDed, so they're referred to as products okay? But we're ORing or summing these two. So this is referred to as sum of products. We'll get into this a little bit more next week. And that'd be written as SOP. The opposite of that is product of sums, and that's a case where we might have something like this. We might have A or B ANDed with C or D. This would be referred to as a product, because they're ANDed together, of sums, two different ORed values. That's just kind of an aside. We'll be talking about that in more detail next week. So hopefully these examples helped a little bit. I'm going to ask you to pardon my kind of the crudity of this whiteboard, but I appreciate your patience as I'm trying to get all this stuff together.